Okay, so this is chapter 2. We're going to be talking about bonds today. Like that. So if you remember back from chapter 1, right, there are 3 basic types of bonds, right? So we have a sort of a covalent bond where the electrons are equally shared. You have an ionic bond where the 2 electrons in the bond reside only on one of the 2 elements. And then you've got this sort of in between, sort of the polar covalent bond, where they are sharing. However, the electrons like to spend more time on one atom than the other, right? So if they're going to spend more time on this side, right, you extra negative character on this side. So it doesn't have a definite positive charge, but it has a partial negative charge, right? So we have partial negative charge, partial positive charge on the other end, like that. So you sort of the spectrum here, like that. So okay. So electronegativity. Okay, so why do they have these polar covalent bonds? It really has to do with the fact that some atoms pull the electrons. You can see the nucleus more readily, and so they're pulled more tightly to that atom. Right. So the most electronegative atom, excluding the noble gases, is fluorine. Right. It's like that. So if you check out the periodic table, you're going to be increasingly the closer it is to fluorine, the more electronegative it is. So fluorine is the most electronegative, cesium is the least electronegative. So if you were going to if you wanted to calculate it, right? So it's really the difference between the bond that determines whether or not the polar character to it. Now it doesn't matter if it's single, double, or triple bond, right? We're just looking between the atoms. Right, so if the difference is low, so hydrogen here it's 2.1, carbon is 2.5, so the difference would be 2.4 or 0.4, right? Which right smack dab in the middle of just a regular. We consider that to be a covalent bond, right? So you have something like carbon-fluorine bond, right? So the difference here is 1.5, right? So that would put it smack dab in the polar covalent bond, right? But if you had cesium fluoride, right? So the difference between is 3.3, right? So that's definitely going to be an ionic character, right? So you only have to look between the differences between these numbers. But really, if you want to think about it, the closer it is to fluorine on the periodic table, the more electronegative character it is. So the farther apart they are, on the periodic table, the more likely it is to be a polar covalent bond. Now, just one thing to note, right? So if you have a bond between itself, so N2, no matter what it is, right? The difference is going to be 0, right? Because there's no difference between the 2 atoms, right? So it's always going to be a polar, or excuse me, a covalent bond, something like that. So okay, so the way that we denote this is with this special cross-hashed arrow, stuff like that. So there's a couple of different ways that we can do. Actually, there's a couple of different ways. To show which one, so if you have something like this, right? So if you have methanol here, right? If you look between these two, which is the more negative, right? So this one here, if you want to calculate it, the carbon is was 2.5. The hydrogen here is what is it? 3.5, right? So the difference is going to be 1.0, which puts it smack dab in the middle of the polar covalent bond, right? So which is the more electronegative? Oxygen is closer to carbon, right? So it's going to have a partial negative charge, so we denote that with a little delta, delta minus, delta plus, right? The other way that you could do it to denote polar covalent bond is actually using an arrow to show the direction of it, right? And then we put a little cross down here to indicate like that's where the positive side is, and it's pointing towards the negative, right? So there's definitely going to be character here. Now you have to be careful, right? Because you think, oh, carbon is always going to be a negative charge, but again, it's always going to be the difference, right? Because we have a lithium carbon bond here, so we have methyl lithium here, right? So this, right? So we said this one was 2.5. Right? Look here, lithium's 1.0. Right? So the difference here is 1.5. Right? So it's a polar covalent bond, but in this case, carbon is the more electronegative, so it gets the minus charge, and this one gets the partial positive charge. Right? So if you would do the arrows, it would go like that towards the negative charge. Right? So this is towards the positive part, and that goes there. Okay. So right. So you just have to look at the difference, how far they are apart. to know if it's a polar bond or not. Okay, so the other thing is, so if we sum up all the differences, all these little arrows for each individual bonds, right, we can get what's called a dipole moment, and that's really it's just averaging all of the little arrows to go here. So like that, and that's usually signified by the little by that little symbol there. But that's so the rules of dipole moments, right? So dipole moment and polar character are two totally different things, right? So like that. So just because it has a dipole moment doesn't mean it's polar, right? So like that's so this is methyl chloride here. So like that says it has a much higher overall dipole moment than methanol, right? But this is much more soluble in water. It's much more polar. So those are two different things. Don't keep students often confuse those, but please don't. Like that. The other thing is electronegativity is about the individual bonds. So this is just talking about electronegativity. You're talking about the difference between two atoms. Dipole moment is the sum of all of the different polar bonds, right? Right. So like that. So those are two slightly different things, right? So like that. So you can have a molecule that has polar bonds, right? But it may or may not have polar or an overall dipole moment. So this is great, right? So this one here, right? This is a polar bond here. But if you have something like the classic case is carbon dioxide, right? So this is right. So it's 2.5. Each one of these is 3.5, right? Right. So here we go. So you get partial positive here, partial negative, right? So if you want to do the arrows, it would look like that. Right? But the average of those two would cancel each other out. So overall, there's no overall dipole, even though it has polar bonds. Okay, so even though it has polar bonds, that's the case. Okay, lone pairs themselves, right? Because they're electrons, right? So they're little negative charges whirling around, right? They're going to give partial negative character to it. Okay, so the classic example is water. Right, so even so this is 2.1. Each one of these is 2.1. Right, the oxygen itself is 3.5. Right, so again, we're going to have the individual arrows going here and here, right? But the overall one is going to be here, right? Because these guys are definitely going to be pulling negative charge here, right? So this is the overall, right? So these are the individual ones, and this is the overall arrow here, right? So even within this, you're going to have that. Okay, that. So, okay. So just be aware of this, of the dipole moment. Okay, formal charges. Okay, so this is actually a record-keeping issue. So like that's of saying, what is the net loss or the net gain of electrons once we assemble molecules like that. So what we really want to do is we want to see how many valence electrons would an atom normally have, and what does it have now, something like that. So, but the trick is to split the bonds. Remember, each bond is worth 2 electrons, right? So we split it in half, and to calculate the formal charge on it, you say, how many valence electrons would it start have, just on the periodic table, right? Minus what it has now, with that, and that'll calculate it. Okay, so for example, so for formal charge, right, here's what we do. So we take something like ammonium, which is that. Okay, remember each bond has 2 electrons in it. Okay, so you split it in half so that each atom in each bond, and one goes with one atom, one goes with the other, right? So if you split this out, the nitrogen would look like this, and each hydrogen would look like that. Okay, so we're just split each bond. Okay, so for the hydrogens, right? So normally they have, right? So they have 1 valence electron, right? Because 1, right? How many do they have now? 1. So the overall valence or formal charge is 0. right? But for nitrogen, right? So how many does it have now? It says start, now, right? So how many does it start with? So nitrogen has 1, 2, 3, 4, 5 valence electrons, right? How many does it have now? 1, 2, 3, 4. Right? So the overall formal charge is positive 1. Okay, so the way we write this is the fact that we will put a plus 1, or just a plus in this case, a plus 1 right next to that nitrogen. Okay. Okay, so if we wanted to do another example here, right? So let's say we had, right? This is a classic example, right? So we're going to take a look at oxygen, this oxygen, and that oxygen. Okay. So again, each one of these bonds, right, has 2 electrons here. So you'd split it in half. So you're talking about that oxygen there, right? You have these 2 electrons, right? So these guys are the lone pairs, right? But it gets 1 electron from this bond, 1 electron from this bond, right? So it's going to be right there. So what does oxygen normally have, right? You count over 1, 2, 3, 4, 5, 6, right? So it normally has 6 electrons. What does it subtract what it has now? 1, 2, 3, 4, 5, 6, 6, right? So the formal charge is 0. So what about that guy? Okay, so again, these two bonds, or excuse me, this bond here has 2 electrons. You split it in half, right? So it already has these 3 sets of lone pairs, which were already included, and then this guy here from the bond, this electron here from that bond, right? So again, it has 1, 2, 3, 4, 5, 6 valence electrons. That's what it normally wants to have. Now it has, you subtract how many it has now, which it has 1, 2, 3, 4, 5, 6, 7. Right? So it has a negative 1 charge, right? So this oxygen should have a negative charge to it. That's how you calculate formal charge. Something like that. So, okay, the next topic is resonance structure. Okay, and this is actually part of this is the fact that the way that we draw it, Gilbert Lewis did a great job in making Lewis structures, but there are some issues with it, and this one is part of this is the fact that we can't always accurately draw what is actually going on. Okay, so this is a way of getting around it. Because if you look at this molecule here, so this is acetate, so this is what smells in vinegar. So what they found is that if you draw the structure for it, right, you should have this carbon-oxygen bond, carbon-oxygen double bond, right? It should have 120 picometers in length. This one should be 135, right? So like that. But what they found, right, so is what they should have is right, it's two bonds in 2 different types of bonds. Well, what they found was, in fact, when you measure this, each of these was identical at 127. It was essentially a 1.5 level bond. Okay, and so it was sort of this one here, where it was the negative charge was sort of in between it, and this was going on. So what they had to do is develop resonance structures in order to account for the fact that it's not necessarily this one and this one, it's actually this one, but this one's really hard to draw. And so what we've done is developed a drawing scheme so that you can take into account the fact that these 2 things sort of exist, but in fact you have to realize that this is the actual situation. Okay, so resonance comes about by the different forms of pi electrons and non-bonding valence electrons. Okay, so what do you need for resonance? You need for resonance. Okay, you need to have one of the following. You need a charge, you need a lone pair, or you need the or pi electrons, right? If it satisfies any of these requirements, it can participate in the resonance structure. Okay, if it doesn't, then if it's just single bonds, if it's carbon with just single bonds, you can't participate. But if it satisfies any of these guys, you're good. Okay, so like this one here, so benzene is a classic case, right? Each one of these carbons is is connected to a double bond, okay, and so they can all participate. And so what can happen is this carbon can have a double bond here, or you can shift these guys, shift the double bonds around so it's actually like this. And so lots of times you'll see me draw it like this, but the actual situation is the fact that it's not each individual one. It's not really double, single, double, single, double, single. It's actually 1.5 that goes all the way around, similarly to what's going on here. Okay, so oftentimes with benzene you'll see it written like this, where these double bonds are actually delocalized. They sort of smear around the hexane here. So, okay, so this is a classic case. You'll see this. You'll see me do this every once in a while. Okay, so rules for resonance. Okay, so we're going to draw these so we can sort of see each individual structure. But in fact, the individual forms are imaginary. It just makes them easier to draw. So be aware of that it's not really any one individual one. It's not really this. Benzene is not really this, nor is it this. It's actually this, right? But it's easier to visualize if we were to draw it like one of these different ways. But these two things are equivalent to each other for just benzene. Each of the individual resonance structures are essentially equivalent, although some, we'll get into more of that later in the course. Okay, again, resonance bonds, only placement electrons of pi bonds and non-bonding electrons. Okay, so rule 2 is it has to satisfy one of these rules, right? It has to have either a charge, a lone pair, or pi electrons involved in it. If it doesn't, don't worry about it. No atoms themselves move. Okay, so you can't. It's just electrons moving, right? If you need to have a hydrogen atom move in order to satisfy the resonance structure, it's not actually a resonance structure. It's an actual just different structure. Okay, so like that. And we're going to use curved arrows to show electron movement, right? So a straight arrow like this shows reactions, right? A curved arrow shows flow of electrons. Okay, so this would be a double barbed would be 2 electrons, right? So 2 electrons. If we wanted to show the flow of just 1 electron, right, we would show a single barb. We'll talk about one thing like that in this lecture. But we're going to use curved arrows, which means the flow of electrons. Okay, so here we go. So here's the curve of electrons, right? So electrons flow, showing how the electrons flow. So they usually go negative to positive, right? So they're showing how they flow. Okay, so here we go. So if we wanted to draw the resonance structures for acetate, like that. Okay, so why would it do this? Well, a couple of different reasons, right? But if these electrons here were to move down here, right? It's a curved arrow. It's two electrons here, right? Carbon already has 4 bonds, right? So it's got to break one. Okay, so it's got to move one out of here, right? It can't break this one, right? Because we can't break a bond. We can't, because that would require, right? Can't break a single bond, right? Because that would mean that these atoms went away. Okay, but the other thing is, since this one has a double bond associated with it, right? These two guys can play within the resonance structure. So what we do, right, is we move these 2 electrons up there. And so whenever we see this double-headed arrow, right? So if we see a double-headed arrow, that means resonance. It would go like this, right? And you'll see this a lot in resonance structures, right? So this set of electrons here became this new bond. This bond here became this new set of electrons. And if you did the formal charges, now it's that oxygen that has the negative charge. Okay? And so why would the molecule want to do this? Well, now, so instead of just this oxygen having to lift the weight of this negative charge, now this oxygen can do it too, right? So we can put part of the time this one has a negative charge, now this one has a negative charge. Like that. So that's what we do. So it helps to stabilize the molecule. The more that we can move this charge, or we can show different structures, it means the more likely to happen if we can move the charge around. Okay, right? So now this guy can't, right? So why didn't I go here, right? This carbon here only has single bonds. It doesn't satisfy It doesn't satisfy this rule, these conditions here, right? It's only carbon-carbon single bond, so it can't participate. However, if we change the rules slightly, okay, so let's say we add a base, and we'll talk about this in a minute, right? I'm sorry, just be CH3, right? So this guy can't, right? So I'm getting ahead of myself, right? So if we have negative charge, comes in and grabs this. Let's say we do a reaction, and so we ended up with this situation. Right? This guy ripped off an electron, right? Hydrogen only needs one bond, right? So what does it do with these two electrons here, right? Because it moves them up onto this carbon. Okay, it's a single-headed arrow, right? So can we do a formal charge, right? Do a resonance structure, right? So it's a formal charge there. Yes, because these guys here can participate. They're right next to this guy with lone pairs, right? So this one can one can participate, right? Because it has a lone pair and a charge. Right? This guy has a double bond, that has a double bond and lone pairs, but this one here, this methyl group down here, cannot participate in it, right? So we don't have to worry about that. So it's just these three atoms here. But again, carbon wants to have 4 bonds, right? So if it lays those 2 electrons down here, that's great for this carbon, but this one has, now it's going to have a 5th bond coming in here. It's got to get rid of a bond, right? So in doing so, it moves that up there, right? So we do a double-headed arrow here. So CH2, C, CH3, okay? So now these 2 electrons here form this second bond there, right? Form that second bond. These electrons here form this new lone pair. Okay, you're going to see this, right? The other thing that you'll notice with this, especially when we're dealing with charges, is that the charges sometimes skips, right? So here it is, oxygen, it skips, and then goes on the next one. Okay, same thing happens here. The formal charge starts off here, it skips this one, and ends up here. You'll see the skipping a lot. Okay. Now, one other thing to know is that just because you can draw it doesn't mean that they're all equivalent. Okay, some things are. There's a difference between which formal charges are possible and which formal structures, which resonance structures are likely. Okay, and so this one is actually much more likely than the 2, even though I can draw them both. Why? Because this one puts extra electrons on the most electronegative atom. Right. So also it's an issue of carbon really wanted just 4 bonds, right? So that's it. But also with that one here, right? So these 2 are possible, but this one is probably the more likely of the 2. Okay, so put that to be around. Just something to keep in mind. Okay, don't forget that your resonance structure cannot violate the valence rules, right? Carbon cannot have more than 4 bonds. It can have 3, it can have 1, it can have 2, it can have 3, it can have 4, but it cannot have 5 or beyond, right? So you need to, you can't go above the octet rule for most atoms, right? So by that particularly carbon. Okay, so be careful. Don't put in that 5th bond onto carbon, right? And the reason why we do this, right? The reason why we're doing these resonance structures is to create stability in the molecule, right? Sometimes this carbon has a negative charge, sometimes this oxygen has a negative charge, right? So I often say it's like lifting a 100-pound weight. If you have one person to lift it, it's going to be pretty heavy. But if you have 2 or 3 or 4 people being able to lift it, it's not so bad. Okay. So this is a way in order to distribute this negative charge around so that more than one the atom doesn't have to deal with it full time. Okay, so drawing resonance structure, right? So resonance structures, right? So we're talking about pi electrons here. They're delocalized throughout the pi bond. So how does this work? Well, if you look at the bonds themselves, these p orbitals are all aligned, right? So they're all in a row. So p, 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 they're all aligned. So you get sort of smearing all throughout. Okay, so like that. So how do you draw them, right? So you have one of 2 choices, right? So here we go. So if we want to, Okay, so if we wanted to, right, so we can move these guys, right? So first thing we should probably do is figure out which atoms could participate, right? So this one's a poorly formed CH3, right? So this guy can't participate, right? Because this one doesn't have a lone pair or charge or or double bond, right? Same with this one here. But all these other ones can participate in there, right? So these two guys are in a double bond, these two guys are in a double bond, this one has lone pairs, so these can all participate, right? So it's just going to be right around in here, right? So you're going to have this phenomenon, again, of lone pairs going to bonds, bonds going to lone pairs, right? So if these guys come down here, right, to make a new bond, a second bond here, right, this carbon's got to get rid of one, right? Because it already has 4, can't add a 5th, right? So what does it do? It moves these electrons there. Okay, so double-headed arrow to show resonance structure, so CH3. Right, so now, right, so that lone pair has become this new bond. This second bond has become this lone pair. Actually, there's a negative charge right there. Now the other thing is, right, so if this lone pair, it could go back here, right? It could fall back on this one and move that up there, but that's just the structure. So let's keep going around there, right? So these guys can fall here, move these guys up, move those electrons up there. So now we get a third resonance structure, right? Right, and now we're out of atoms that can participate in our resonance structure. So we're done. Okay, so this one can actually have 3. But again, notice we have this with the formal charge, we get the skipping phenomenon. We have oxygen, you skip this one, go here. This charge skips here and then goes up there. So just something to be aware of. Okay, now the other option we could do is so here, right, we did full arrows, right? So we did, which meant we have 2 electrons moving around. The other option is to do single-headed, is to just move 1 electron around, right? So now if we have something like this, right, again, right, if we have an electron here, right, right there and right there, right, so remember each one of these has an electron on it, has 2, each of these bonds can participate. Right? So this one, okay, it doesn't have a lone pair, but it does have an extra electron. Right? So, okay, so if we wanted to make a new bond here, okay, so remember this one actually only has, right here, let me draw on the hydrogen so it's a little bit easier to see. Okay, this one only has 3 bonds, right? Wants to have 4, right? So what it does is it really like to put a second bond here, but it doesn't need this full, both of these electrons. It really only needs one of them, right? It only needs that one. Right, so what we do is we say, okay, I'm going to mix this 1 electron with this 1 electron here, right? We only did single barbs to show that, right? Now we've got a bond here, right, from this electron and that electron. So where does this go? Well, just like this one pushed it on to here, right? We're just going to push that there. Okay, and so now we have this. Okay, and so this is that bond that we just created, right? And that's the electron, that's this electron here, went there. Now the other option, right, these 2 carbons can participate, so you can take, right, one of these electrons, right? It only needs 1 of them, right? So now we can move, if we take our lone electron, move it there, right, to make this one and this one, we can make a new bond here. So what does this go? This goes right there. So we can make this. And so it doesn't really matter if it's 1 electron or 2. It's still going to behave very similarly. Okay, so this was the new bond we created, and then this was the second new bond that we created, and this electron here had to go somewhere, so it ended up, can't just float in space, so it ended up on that carbon there. And if you actually do the formal charge, there's actually no charge there, right? So that's you can do that in your spare time, right? So, but these are the 3 resonance structures. We're at the end of our available atoms to work with with the resonance structures. Okay. Okay. Now on for something else, right? So so now we're actually going to talk about acids and bases, right? There's two different classes of acids and bases. The first one being the Bronsted-Lowry definition. By that one, and this one is specific, but we'll be using it quite a bit. And in this one, what we're going to say is an acid. It's all about H plus, or I'll sometimes call it a proton, right? Because it's a hydrogen charge without its electron, right? It's just a proton. So okay, so we have an acid donates its H plus, right? And a base accepts H plus. Well, think about this. Okay, you've seen this, all throughout general chemistry, right? HCl, right? So, right, this is an acid, right? So what happens when you mix it with OH minus, right? This is, we know, as a base, right? So it's like sodium hydroxide, right? Potassium hydroxide, right? What happens? This comes in, grabs this, right? So you can sort of think of it, this as sort of a big hand, right? It's coming in and grabbing it, right? And what do we make? We make Cl minus, right? And H2O, right? You can always think of H2. H2O is lots of times it's easier to think of as HOH, right? So HCl is a classic example of an acid, of a Bronsted acid, right? It gives away an H, right? So it has one available. Sodium hydroxide wants an H to make water, right? So it's what you get. So don't overthink it, right? Just think of HCl and hydroxide. Okay, so but do remember from general chemistry, right? So if this is the acid, right, the corresponding one on this side is considered a conjugate base. Okay, this one on here, if this is a base, then over here, this is the conjugate acid. Okay, I always joke my students that it's they just did this to it makes sense, but it's to screw with the general chemistry, the freshman chemistry students, just screw around with the naming. Okay, but this becomes important later, right? So here, this would become, if you run the reaction backwards, right? This one is the base. This would come in and grab. This one would come and grab that hydrogen, right? So this now it's acting like a base because it's grabbing it, right? So that's where the name comes from. Okay, okay, so you can do with equilibrium constants, right? So you have products over reactants, right? So why isn't water in here, right? See the concentrations, right? So the coefficients out here are actually the exponents out there, but everything's 1, so you don't have to worry about that. So why isn't that there? Back from general chemistry, it's pure liquid. Water's pure liquid. We don't include pure liquids or pure solids in here because the concentration is fixed. So like that. So and then pKa is actually just the negative log of this, right? So if we had H in here, right? So if we just isolate that, right? So we have the pH, something like that. So the pKa, this, right? So maybe we go back, the pH is up like that. So like that. So for nitric acid, the Ka is this. So we can plug that value into here and get the pKa is negative 1.3. Right? So not too bad. Right? Just shades from general chemistry. Okay, but one thing to remember is that if you have a strong acid, and that means your corresponding base is terrible. Right, so it's this balancing act. If we have a strong acid, we have a terrible base. If we have a weak acid, we have a great conjugate base. Right, so that means that if this is a mediocre acid, right, that means its corresponding is a strong base. Right. Oops. Okay, so this is a strong acid. That means its corresponding conjugate base pretty terrible. Stuff like that. So it's this inversion of it. So, okay, so can we predict a reaction by looking at the pKa's? And the answer is yes. Right. So that's so what you really want to do is you need to compare the acid to the conjugate acid, and specifically the pKa. Okay. So like that. So what you want to do is you want to go from a low pKa acid to a high pKa acid. Okay, so you can use this chart. You could use this chart if you wanted to. Okay, so here we go. So if we have, so if you go HB, HA plus B minus going to H minus plus HB, right? We're going to look at the pKa of this and this. Okay, and we want it, right? So, right, we want it to get bigger. 1, 2, to get bigger. Right? So which way is it going to go? Right? So if this is, so in this case this is low, this is high, right? So you want it to get bigger, right? So does 25 to 35, so the reaction is going to go forward, right? So 25 to 35, right? The reaction wants to get bigger, so that means the reaction is going to go that way. Going from 2 to 4, reaction gets bigger, it's going to want to go that way. Okay. From 12 to 10, you want to get bigger, so the reaction is going to run that way. That's the natural way it wants to go. Okay. Okay, so there you go. It wants the pKa wants to get bigger, going from product to reactant. Easiest way to figure this out. Okay. Okay, so for organic acids and bases, okay, so again, we're going to be using the same concept of hydrogen coming and going, right? So that's so a molecule with just some sort of, so consider that if its pKa of its most acidic hydrogen is maybe 25 or less, it's considered acidic, right? So methanol is fairly acidic. Acetic acid, obviously, as the name implies, acetic acid, it is acidic, pKa about 5. Acetone, yeah, fairly acidic, right? It doesn't take much to pull off one of those hydrogens, stuff like that. So this is kind of fairly acidic as organic molecules go. So why is this why is this OH much more acidic than this OH, right? They're both OHs, right? Well, it has to do with the conjugate, the resonance stabilization. After the base comes in, right? It comes this, you can form the stabilization. If you can form resonance stabilization, that means it's more likely to happen, right? So it's okay. The molecule is much less resistant to it happening, right? So no big deal. So it can go fairly easily. So you don't have this resonance stabilization on this one, so the molecule is much more resistant to it happening, right? And actually this one here, this CH bond here is very, very low as far as pKa compared to a regular carbon-carbon bond, say like methane. Why? Because you can do resonance stabilization in here, right? With this one here, so that means that carbon-hydrogen bond is much more likely to pull it off. Okay, so organic bases, right? So they're gonna have a lone pair of electrons, right? Because they want to make that new bond, right? So if you think about, right, classic organic acid, right? So negative charge here, right? So if you have HCl, right, organic base, you're going to take 2 of these electrons and attack the carbon, or attack the hydrogen to make a new bond, right? So you make, right? So these 2 electrons becomes this new bond here. But hydrogen only needs to make 1 bond, right? So what does it do with these 2 electrons? It puts them onto there, right? Already has 3, so plus Cl. Right? So these 2 electrons become these 2 lone pairs, right? No big deal. And the formal charge is negative. Okay, so organic bases are going to have a lone pair, and typically, and they can sometimes have a negative charge, right? But they're definitely going to need a lone pair, right? Because they need that lone pair to make the new bond with H plus, or with the hydrogen, right? They're going to use this lone pair to make this new bond there. Okay, typically they have a negative charge. Okay, so acids, right? They're going to have that, right? So if you have an acid, right, you're going to have that pKa, a readily available pKa, or a hydrogen with low pKa. So that's okay. Now you can have molecules that have both an acid and a base within them, right? So now it's got a positive, right? So if this hydrogen, if these lone pairs come in and grab that, snatch that hydrogen. Now, if you do the formal charge, now this one has a plus charge. This is the same molecule. If they have a plus negative charge on the same molecule, it's called a Zwitter ion. You sometimes see that, like that. Every once in a while, quickly in things like this, like amino acids, you see that. So now, Gilbert Lewis came along and said, let's make this a little bit more. Let's make this a little more general. Okay, and so what it's actually doing is instead of just saying the hydrogens, right? Let's just say these lone pairs, right, are going to attack, these lone pair electrons are going to attack something that needs lone pairs, right? Doesn't matter. It doesn't have to be H. It doesn't have to be H+. It can be anything you want, as long as it needs those electrons, right? But it's this lone pair of electrons coming in and attacking something that wants the lone pairs, or wants a new bond, okay? And so you can have things like this, right? So Lewis acids don't have to be H+, but they're typically going to have a plus charge to them, right? So this one here has a magnesium is a Lewis acid. It has a plus charge. This is a Lewis base. It has a negative charge, just like a regular base, right? But it can accept this, right? So these negative charges can come in and donate their lone pairs of electrons, right, to make new bonds to magnesium. Okay, you can have boron. It has, if you look at this, right, it only has 4 valence electrons, right? It has an orbital open that it needs to get the octet, right? So if you have something like this, right? So if you have an ether, this guy here can put its electrons there to make a new bond, just like this bond up here, right? So you can make right, and if you do the formal charges, boron now has a negative charge, and this oxygen has a plus charge. But all we did is turn these 2 electrons into this new bond. Now everybody has their octet, and everybody's happy. Okay, so it's no different between Bronsted and Lewis. It's just Bronsted is specific to hydrogen. Lewis is much more general, but it's the same concept. Lone pair coming in, attacking something that can accept those electrons. Okay, so last part, some non-covalent interactions. Okay, so what you know about these more than you know. You might have talked about these in general chemistry, but they can be important. One, you can have what are called dipole-dipole interactions, and these are ones where you have polar character within the bond, right? So you have partial positive, partial negative charge. What can happen is these guys can line up, right? So the positive, negative, positive, negative, positive, negative, line up like they should, right? So these things can work pretty well, right? So even whether formally or informally, right, we can get that. The other thing we can get are actually these very spontaneous and very instantaneous positive and negative charge, even with molecules that don't have polar bonds. Okay, so this was discovered by Fritz London. He's a Duke chemistry professor. He would have won the Nobel Prize, but he died before he had a chance. But what he noticed, these what are called London dispersion forces, is that what will happen is if suddenly the electrons happen to be on this side of the molecule, what will happen is you'll have a partial negative, partial positive one here. That will induce all the other molecules to get these, right? So the electrons over here will repulse the electrons over here, which will move them over there, which will cause this one to move them over there, move these guys over there. And so you have, even the things that have just purely covalent bonds, like oils, right? You're going to have this spontaneous of dipole moments in them to react. And it's fairly weak, but this is what explains why oils can be either liquids or solids rather than just all gases. It's this induction of a dipole moment that becomes important in the keeping the molecules together, or associated with each other. Okay, the other one that we can do is exceedingly important, particularly in biology, and these are the hydrogen bonds. And this is where you have a hydrogen that's on something electronegative, so a nitrogen, hydrogen, oxygen, hydrogen. Right, so you have a definite polar covalent bond here. It's going to be attracted to lone pairs on another molecule, right? So you have, So you have a partial positive, partial negative charge here. This hydrogen is going to be attracted to the lone pairs, which are going to have, because they're electrons, they're going to have a partial negative charge to them, right? Something like that. So over here, so like that. So where do you see this, right? In water, in keeping double-stranded DNA together, right? So in between here is what's keeping their strands of DNA together are hydrogen bonds. They're fairly weak, but when you add up a whole bunch of them, millions and millions and millions of them together, they become very strong. You also see this in biology with beta-pleated sheets, right? And alpha helices and keeping protein secondary structure together, right? So you have these hydrogen bonds keeping that structure together. Okay, and then two terms you need to know just pop up at the end: hydrophobic, hydrophilic, right? So this is hydrophobic, right? Things that dissolve in water, and hydrophobic, which are things that don't, right? So you can think of your Greek roots: hydro, water, philic meaning loving, right? So it loves to be in water. So something so small alcohols, ketones, things like that. Hydrophobic, right? Water hating, right? So things that don't dissolve in water, right? So these are nonpolar. So these are oils and fats and things like that. So two terms to know: hydrophilic, hydrophobic. There you go. Thank you.